Great, thank you. I think the mic is working, yeah? All right. So yesterday I tried to give an introduction to prismatic homology, and I mentioned some of its applications. And so the plan for today is to go into more depth into one of these applications, which is in algebraic geometry. And so the application is concerned with, sorry, this water, vanishing theorems. And so let me just make that the title. And so in complex algebraic geometry, there's an important vanishing theorem in Chromology called the Chordera vanishing theorem. And essentially, the goal of today's talk is to tell you so the Chordera vanishing theorem is, the proof uses Hodge theory. It's really an analytic statement. And it's very useful in complex algebraic geometry, but it has no the obvious counterpart, if you're not working in characteristic zero, is just false. And so the goal of today's talk is to tell you some salvage which has emerged over the last few years for this result when you're not in characteristic zero. But let me sort of begin with the classical story. So classical Chordera vanishing. And so I think the theorem goes back to the 50s. And so I will formulate it in the language of algebraic geometry, although maybe I think originally there was a more analytic formulation. So x over the complex numbers is a smooth projective variety. So it's something sitting inside projective space, and then it's also a manifold. And then the vanishing concerns certain cohomology groups attached to X, but also attached to a line bundle on X. So I give myself a line bundle on X which has some positivity property. So an algebraic geometric way of saying that is that it's ample. For instance, you can imagine X is sitting inside projective space, meaning you choose an embedding, and then you take the tautological line bundle on projective space, the bundle of lines, O of 1, and you restrict it to X. And then in this context, the result is that cohomology in degrees less than the dimension of X with coefficient in the inverse of L, the inverse line bundle, vanish. And there's an equivalent formulation, which I'll squeeze in over here, which is if you look at cohomology in degrees bigger than 0 of X with coefficients in not L inverse, but rather L, but then you have to twist it by the bundle of top differential forms, the canonical bundle, this has to vanish. These are related by Serre duality. And so this is the basic vanishing theorem that I want to focus on in this talk. It has a lot of uses, and I'm not really going to get into the uses here, but let me at least give you a flavor of why a statement like this about higher cohomology groups can be useful, even if you might not care about higher cohomology groups at the end. And so here's a sample use. Basically, I'm going to try and tell you that it allows you to solve certain inductive problems, induction being the induction on dimension. So if H inside X is a divisor in the linear system defined by L, so if you're imagining X inside projective space, I'm just taking a hyperplane section, then this version of the theorem has a consequence about global sections, which is the following. So H naught means just globally defined sections of the corresponding bundle. So I can look at the canonical bundle on X and twist it by 2H, which means you look at those top forms which have poles of order at most 2 along this divisor H. And this has a residue map to something analogous on the divisor, but the order of the pole drops by 1 when you take the residue. So it goes down to h. Sorry, omega h, not x. So if you squint a little bit, this is going from sections of the canonical bundle on x to sections of the canonical bundle on h with some pole condition. And then the statement that you get out of the theorem is that this is surjective. Because if you sort of chase the long exact sequence, the obstruction to being surjective would be an h1, which is annihilated by this theorem over there. And so what this lets you do is that if you get, like, a kind of problem you might want to solve in algebraic geometry is produce lots of sections of the canonical bundle in certain situations. And this result says that if you can find sections on the divisor, you can often lift them to x, provided you have these decorations in place.
What is omega h of h?
What is omega h of h? Sorry, this h just means tensor with L. So, what I really mean is I take O of h on x and then restrict it to h. Yeah, so maybe it's worth saying that. So this is the result, and let me also very briefly tell you what goes into the proof, mostly to indicate why, even though the statement looks like it's completely algebraic, the proof is not a purely algebraic thing. It's just something transcendental. So the idea of the proof is you try to use some Hodge theory to translate what this vanishing means, which is a vanishing happening sort of in the world of algebra, meaning, so this is happening in the world of coherent sheaves, and if you like, I could have stated this entire theorem in the language of graded modules over graded polynomial rings in some super concrete way. It has nothing to do with any topology, but you translate it into something which does have something to do with topology, and so you use Hodge theory to translate to the following statement, which is, I'll just tell you what the output of the translation is, not how you get there. So homology in degrees less than or equal to the dimension with compact supports on a smooth affine variety with complex coefficients is 0. So there's some non-trivial Hodge theory that goes into going from this statement to this statement. But the statement over here is a purely topological statement about an affine variety. You take an affine variety and you think about its cohomology with compact supports, which if you could use duality to get rid of the compact supports if you want. And then this is something you can just ask about, like the shape of the affine variety, and it's known to be true. So this is Artin vanishing. And if you're thinking more analytically, this is Andreotti-Frankel vanishing. It's a statement that if you have a smooth affine variety over the complex numbers of dimension d, then it has the homotopy type of a CW complex of dimension d and not 2d. And so that's kind of the story with Chordera vanishing. As you see, the proof is definitely not algebraic, and let me just emphasize this by a remark saying the theorem definitely fails. Away from Kersig 0. Meaning, if I replace the field of complex numbers over here, let's say a field of Kersig P, or even something that's called a mixed characteristic, meaning something like the integers, the theorem is false. Counterexamples of, in the Kersig P case, the first counterexample was written down by Michel Reynaud. And in the mixed characteristic case, Bert Totaro provided some examples.
But in Kersig 0, there is still no algebraic proof?
I mean, not as far as I know. I think there's an algebraic proof through Deligny-Lousy. which is going to characteristic P and using some kind of mod P Hodge theory.
There is such a
There is such a proof. And it's not going to be, in principle, that far from the rest of my talk. I'm going to try and do a p-adic analog of the way we will see.
So the second statement is algebraic, right? Because the homology is zero.
Correct. So sorry, I forgot to repeat the question. So Paul's question was the second statement that I translated to is algebraic. Absolutely, yeah. It's just that the process of translating uses, yeah, something transcendental. Other questions? Okay, so let me now talk about what happens in mixed characteristic. And so I guess I'll call this KV, Chordera vanishing in mixed characteristic. And I'll just sort of write down the theorem, and we'll spend some time unwinding it. So let me call this theorem KV for ease of reference. This is from 2 years ago. And it's the following. So x is now going to be over the p-adic integers rather than over the complex numbers. Again, well, I don't have to actually assume smoothness anymore. So let me just say project proper even is enough. And flat. If you don't like these words, feel free to assume smooth and projective. And I want to give a name to the dimension. So of relative dimension D. And then L is as before. Ample. But in fact, you can weaken it, and this is often useful in applications. So there's a, I'll just write it. It's called semi-ample and big is enough. So semi-ample means that it's globally, some tensor power is globally generated. And big means that the map it defines to projective space, while not an embedding, will at least be birational. So it's generically an embedding, but it might collapse some stuff. And so in this setup, we want to try to understand the analogs of these groups. And as I was saying above, they can definitely be non-zero. But there's a salvage, and the salvage is the following. So I guess I'm going to go over here. So there exists a finite cover. So a finite surjective map pi from y to x such that the cohomology classes that you do not want to be there will die when you pull back to y. So let me write it this way. Pi over star is the zero map. Right, so it's not saying that this group is zero. This is torsion. I mean, this isn't, the statement is only interesting for torsion classes because if you try to ignore torsion, then you can just use the characteristic zero statement. And so what the result is saying is that, right, the torsion classes are not necessarily zero, but any individual torsion class, or in fact all of them, because there's only finitely many, can be annihilated if you pull back to a particular finite cover. What it's not saying is that you can find a finite cover for which this group is zero. Like there might be more classes you created in the process. And in fact, that happens in examples. You can never find like a single finite cover where everything just becomes zero. But in applications, that's OK, because in applications, you're often trying to, the way these classes come up is it's an obstruction to solving some geometric problem. And if you can kill it after going up to this finite cover, it means you can solve your geometric problem after going up to a finite cover. And that's often good enough for things you want to do. Well, in any case.
So here you don't have to use it. So in case zero, this is already more general than what we explained before. What happens?
OK, so the question was, in theorem KV, I did not assume smoothness, whereas in the original version I did. And so am I actually getting some new consequences in characteristic zero? And the answer is no, because I'm only talking about torsion classes.
There is no statement about the non-torsion.
So there's a better version. I mean, this was the simplest version I could formulate here. There's a better statement where I don't put a torsion here or here, And then the conclusion you get is that any individual class becomes divisible by p when you pull back. So somehow p-adically the class is becoming small. But it's not becoming 0. It's just p-adically small. Yeah. OK. So a good question again. So the question was, why is there a star over here and not a star over here? And so it turns out that if you put torsion, then it doesn't matter because of some long exact sequences, like Bach-Steins. Correct. So Roman was asking about the more general statement that I just alluded to, and yeah, in that case you would have to put you would have to restrict away from the top degree.
If you have x which is but does not have a peak characteristic 0, then this is fine.
Okay. So the question was, what happens in characteristic P? And I'm about to allude to I'm about to mention this. So there's an analogous statement in characteristic P that was known before, and that was kind of the model of what inspired this theorem. So theorem KV in characteristic P, meaning I replaced, if I replace ZP with the field of characteristic P, was known before. It was essentially, it is the work of Hoxter and Hunicke. So they, for like several decades in the second half of the last century, they were developing this theory that's now called F singularity theory, Frobenius singularity theory. And this was kind of one of the basic important results in that theory in the characteristic P setting. Again, there was some, so they did the ample case, and then the semi-ample and big case was in my thesis in characteristic P. But yeah, it was definitely known before. The other question I get whenever I talk about this is the map pi like a covering space, or can it ramify? And it definitely ramifies. So it's typically ramified.
Do you explicitly produce the pi?
Right. So the question was, do I explicitly produce the pi, or do we actually do some more general thing? And we do not explicitly produce the pi. So that was going to be my third remark. This is great. So the proof is not effective at all. The way the proof works is, instead of thinking about any individual finite cover, you try to think about the structure you would have if you take the inverse limit over all finite covers, and what kind of a scheme that is and what properties it has, and prove something there. And then there are some approximation arguments. They say that if you can kill everything in the limit, then they actually die in some finite extension.
So there's an infinite level statement.
Correct. If you take the inverse limit of all pi, then you would get an actual Chordera vanishing for that.
Oh, yeah.
Other questions while I erase? Uh-huh. So the question was, where is this proof of the vanishing theorem explained? I think this is essentially explained in Rob Lazarsfeld's book on positivity in algebraic geometry. Or at least that's where I learned it. Sorry? But Andreade Frankel was right. This is not Chordera's proof. Right, right. Yeah, sorry. This is an ahistorical presentation of these ideas. Yeah, somehow like the proof I had in mind was to translate there's some Hodge theory for open varieties, and if you run it for a smooth affine variety given by the complement of a hyperplane section, one of the sort of some ends in the Hodge decomposition will be the term showing up in Chordera vanishing.
So when you say characteristic P was known before, characteristic P everything is a torsion, right? So
Yes.
you just don't put stuff in torsion. Yes. So
Sorry.
what is the state
In characteristic P, you don't put torsion, but then you have to restrict to less than or equal to the dimension. The flatness hypothesis is doing some work in allowing me to put work in all degrees there. Great. And so I just wanted to mention one application of this, which I kind of alluded to yesterday. So vanishing theorems are often useful in birational geometry, and this was somehow no exception. So theorem KV was used in the proof of the following. So
One more quick question. So the degree of this cover, does it have to be a power of P or something like that?
question was, does the degree of the cover have to be a power of P? Well, at least P has to divide. I mean, the pullback is, so if you assume X is normal, then pullback along finite covers will be injective if the degree is co-prime to P. So there have to be lots of P's in there. I'm not saying if it's just a power of P, but there's at least P's in there.
But does there exist a pi whose degree is the power of P for example?
I believe you can arrange for such a pi by some Galois theory. You first find a big one that works, and then mod out by some CLOs. I didn't think about it super carefully. Yeah. Right, so, I mean, okay, I'm just going to state this vaguely. So one can run the MMP, the minimal model program, for arithmetic threefolds, meaning threefolds that are not necessarily defined over a field, but the residue characteristic has to be at least 5. So for example, a threefold over Z7. And there's a lot of authors, so I didn't write out the names. That's Linchon Ma, Joel Patak-Falvey, Carl Schweid, Kevin Tucker, Joe Waldron, Jakub Witeczek, and then Takamatsu and Yoshikawa. Okay. And so this was kind of, I mean, I don't know, it was a nice application of the stuff, which was not inspired by really thinking about these applications, but more just trying to understand this result better. And so the goal for the rest of my talk is to, obviously I'm not going to like sketch a proof, but I would at least like to give you some idea of why a statement like this what it has to do with prismatic homology, which is what I was talking about in the first talk. And essentially there are two ingredients in the proof. One is prismatic homology, which connection I will try to explain. And the other is some version of a Riemann-Hilbert correspondence for mod P sheaves, which seems interesting, and so I'll try to talk about that at the end of the talk. But first, maybe what I'll, the first order of business is going to be to get rid of all this fancy stuff and translate this into a very concrete statement in algebra. Let me be safe. Okay, so what I want to do first is I want to translate this statement into just some statement about local rings. And there's a sort of standard way of doing this. And I'll just try to explain this using a picture. So maybe the picture can fit over here. So let's say, this is over the complex numbers. So let's say X over C is a smooth projective variety. It's actually embedded inside projective space. I guess it won't fit, okay. So in this case, there's a sort of singularity one can attach to this situation. And the local geometry of the singularity sort of faithfully reflects global features of X. And the way this works is very simple. So here you have X. What you can do is you can look at the total space of the tautological line bundle of lines on X. So it's O of -1, I think, if you're doing the normalizations the way I do them. This is the projection map. And of course, there's a 0 section over here. That's for any line bundle. And since I chose this particular line bundle, the 0 section actually has negative self-intersection, or if it was it's extremely negative, so it can be collapsed. And so there's a birational contraction where the output looks like the cone. And in fact, it is the affine cone on X sitting inside AN plus 1. And so my original X was inside Pn. And the cone sits inside AN plus 1. And the 0 section goes to the singularity. Let me call it 0. And the basic kind of principle is that global cohomological properties of X they're faithfully reflected in what's happening in a small neighborhood of the singularity. And that's at least believable if you look at the picture, because if you look at the picture, take a small neighborhood of the singularity and then remove the singularity, it basically just looks like X cross, something like an open subset of the complex numbers. So it's more or less just X. So these are local properties of the cone at 0. And so if you go through this dictionary, the global cohomological vanishing over here gives you some kind of a local cohomological vanishing on the cone. And that statement turns out to be general in that it's not specific to cone singularities. It applies to any singularity. And so I'm going to try to just formulate that. Because one advantage of working with rings rather than varieties is you can use elements much more easily. And so here's the element version of this Chordera vanishing theorem. So I'll call it theorem KV log. And so here's what it translates to. So say R0 is a polynomial ring over the p-adic integers, Zp adjoin x1 through xn. And I choose something bigger called R, which is a finite extension. So this just means R itself is finitely generated as an algebra over the p-adic integers. And moreover, each of those generators satisfies a monic polynomial over R0. So you've done something like, extract the square root of x1. That would be an example of such an R. And such maps are called Noether normalizations, and they exist in abundance. And so in this setup, the theorem is going to say the following statement. So then there exists a further finite extension, R to S, with the following property. And so the property is going to try and capture these cohomology groups that were showing up in Chordera vanishing. And here's at least one way to say it. So any relation of the form summation ai xi is equal to 0 in R mod p. So R mod p has these elements, x1 through xi, and they might not sort of be independent anymore. There might be some relations between them. So if you had such a relation, ai xi equals 0, then it becomes trivial in S mod p. So trivial here means it's more or less it's a linear combination of the most obvious relations you can imagine, which is xi xj equals xj xi. I mean, those are certainly relations that are going to always be there, and linear combinations of those will be there. And the statement is saying that after you go up to this larger extension, any such relation becomes trivial. And so that's, if you like elements, that's a super concrete version of what this Chordera vanishing theorem says. Maybe a slightly highbrow formulation of this, which is useful in thinking about it, is the following. So if you look at this is in the direction of what Daniel was asking. So what happens if you think about all finite covers at once? So let R plus be the integral closure. It's the union over all such S's, basically. So it's the integral closure of R in an algebraic closure of its fraction field. So it's the biggest finite extension of any ring you can build. And then the theorem is going to say that mod p, any relation in R plus is actually the trivial relation, which means
So all these rings are integral domains, right?
all these rings are integral domains. Yeah. And so the statement is that R plus p-adically completed is Cohn-Macaulay, which is essentially this property of having no interesting relations. Okay. So if you would like me to be more formal about what relations mean, then you can think in terms of Koszul homology, which is some algebraic construction that sort of gives a name, gives a home to these relations modulo the trivial relations. And then the theorem is saying that the map from the Koszul homology of R mod p to that of S mod p is a zero map. Okay. So that's the theorem. I want to make some remarks about this and then talk a little bit about what goes into it. But I want to emphasize that the statement is extremely elementary, and the proof uses everything I know about p-adic Hodge theory. And it would be really nice if there was a way to do it without all that machinery, already for n equals 2. So if someone has any ideas, I'm all ears. Okay, so the first remark is, I guess, this is definitely a mod p or a p-adic statement, meaning if you could replace zp with the complex numbers and try to formulate a similar statement, it would just not work. It has to, like, this process of killing relations by finite covers is not very useful in characteristic 0 because you can trace back down whenever you have a finite cover. So it's only, it's a feature of not being in characteristic 0. So maybe let me just write it. Theorem kv log is widely false in character 0. And the second remark is similar to this remark over here, and it's essentially the same remark. So this theorem was known in characteristic P by the same authors in the same paper. And I mean, if you look at their paper, you're not going to find the geometric formulation that I explained before. This is the version you'll find. And it has a lot of applications to singularity theory in characteristic P. And similarly, this theorem sort of FP. Yes.
But this is the same as making another way.
Sorry, no, ZP is replaced by FP. That's what characteristic P means. So P becomes 0 now. Yeah.
But what does it mean? So there is no R mod P.
Well, R mod P is just R in that case. Right. What was I going to say? Right, so just like this kind of characteristic P version had a lot of applications in algebra, so does this version. But maybe I will not spend too much time spelling them out. I'll just say that there's an open question in commutative algebra called the direct Subman conjecture, which was open for like 50 or 60 years. It was solved a few years ago by Yves André. And this result gives a very cheap proof of a more general statement. No, so, well, probably at the time it was, but I think nowadays you can prove it in a few lines, or at least in a few pages. And I'll actually try to sketch what they do, and then tell you where prismatic homology comes in and carrying out the same outline in characteristic 0, in mixed characteristic. Between what? Oh, it's the 0 element of the Koszul complex on the x-size. Yeah. Okay, so yeah, let me comment briefly on the strategy. And this is also, the strategy I'm about to explain is really a strategy for proving the theorem in characteristic P, adapted to this mixed characteristic case using the prismatic stuff. So the very rough strategy it's just going to be 2 steps, because I can't do more here, is the following. So you have this ring R you're trying to prove something about. And all the information that you're trying to capture is sort of local near the xi. So it's sort of, you only care about what happens when you localize at the xi's. So let me formulate a local statement. So say R comma M is, so technically speaking, it's a Noetherian local domain. P is in the maximal ideal, and D is the name for the dimension. You can just take this R to be the localization of that R at the ideal generated by P and the xi's. And so the goal, if you're trying to prove some annihilation statement for Koszul homology like so, is the following. So we want to annihilate some group that measures these bad relations by finite covers. And I could use Koszul homology, but let me use something called local cohomology by finite covers. So this is the theory of local cohomology that Grothendieck invented. It's essentially a direct limit of what happens with Koszul homology when you replace the xi's by their powers. For the purposes of this talk, it's not going to matter that much. It's some group that captures whether or not there are such bad relations. And so in characteristic P, the way they proved this theorem, or one way to understand the proof now, is by an induction on dimension. So you first try to argue by induction on dimension that you can find a finite cover where the map is not quite the 0 map, but the image is very small. And then small technically means finite length. And then once you're in the finite length situation, you use the fact that there's a Frobenius that acts on everything in sight to further annihilate those finite covers, finite classes. And so if you want to do something similar over here, you're going to get stuck at step 2 because there's no Frobenius in mixed characteristics, right? If I take a ring of like ZP and I look at the map x goes to x to the p, it's not an additive map.
So when you say dimension, is the dimension of a ZP?
It's just like the dimension as a domain. So as in like Krull dimension. So maximal length of chains of prime ideals. In that situation, the dimension would be n plus 1. N for the variables, and then 1 for ZP. And so to sort of carry this strategy that I was just sketching out in mixed characteristic, the first idea was to replace the ring R showing up in this goal by something which has a Frobenius. And that's where prismatic homology comes in. So star is equivalent to star prime, which is the statement that you want to annihilate h less than, there's a d plus 1 now of the prismatic homology of R by finite covers. So the fact that there's a d plus 1 instead of d is a reflection of the fact that in the definition of prismatic homology, or in the little I told you about it yesterday, there was this extra parameter u that was showing up, which is sort of an extra arithmetic direction. And the plus 1 is somehow accounting for the fact that prism R roughly has dimension d plus 1 if R has dimension d. This is a complex now. It's a prismatic homology complex of R. And then step 2 is to prove star prime using 2 ingredients. So induction on dimension, just like they did in characteristic P. But if you just try to naively copy this argument, you'll run into a problem because the ring had dimension d, so you only somehow have d many directions to play with. But now you've introduced this extra arithmetic direction, so you need some extra ingredient to handle the induction in the arithmetic direction. And that extra ingredient is the p-adic Riemann Hilbert correspondence. So and so my plan for the rest of the talk is to actually just tell you more about the p-adic Riemann Hilbert thing and forget about everything else that came before. But this is very roughly sort of how prismatic homology fits into the picture. Roughly, it allows you to sort of replace rings where there's no Frobenius actions with objects where there is a Frobenius action, so you can carry out some arguments that you might be used to from Kersig P, where there Frobenius acts on everything in sight. Okay. Sorry, are there any questions?
In this theorem, is it possible to replace it with form of power series?
Yeah.
Equivalent?
Right. So sorry, the question was how much flexibility do you have in this theorem with changing R around? So there's a completely general statement for any Noetherian excellent ring that has a dualizing complex.
I'm just trying to compare what you just said. So you're saying you want to be in a setting where Frobenius exists. So this set of this p-adic Riemann Hilbert achieves that because there is a Frobenius on the constructible side, or is it?
No. So the Frobenius is basically what's happening in step 1, where I replaced R with the prism of R. So this guy has a Frobenius. Maybe I should emphasize this. Somehow one of the defining features of prismatic homology is that it carries this Frobenius action. And so you want to exploit that. And then the Riemann-Hilbert thing comes in when you handle the induction on dimension to somehow account for this new arithmetic parameter u that you introduced in the definition of prismatic homology. Like this is really a d plus 1 dimensional ring, and you get sort of d directions of freedom coming from R, and then 1 comes from this arithmetic guy, which the p-adic Riemann-Hilbert thing will. So, it will help you prove the thing you need to prove to handle the inductive step in that direction. Sorry, this is not a very super precise thing. I'm just trying to give you some flavor of what's going on. I'm happy to explain more. Yeah, sorry. So the question was, can I repeat what I said before about what kind of rings that are allowed? So maybe the first observation to make is that the statement really only depends on R. R0 is just some it's essentially an auxiliary thing that allows me to talk about the Xi's. The Xi's could be any regular sequence in R. It doesn't have to be these particular ones. And so the general statement is that if you have any Noetherian excellent domain R with a dualizing complex, there is a finite extension R to S such that the induced map on Koszul homology groups with respect to any regular sequence is the zero map. Okay, so p-adic Riemann-Hilbert. So this is all joint work with Jacob Lurie. It builds on a lot of previous work in p-adic Hodge theory by various people. But let me at least mention Faltings, Scholze, and then Rochon Liu and Shinmen Zhu. I mean, somehow they figured out what the picture looks like for local systems, meaning what happens under Riemann-Hilbert to p-adic local systems. And what we need over here is a version of that for perverse sheaves rather than local systems. And so that's what we were trying to do. And so here's the setup. So I'll try to formulate statements geometrically, meaning I don't want to worry about arithmetic complications right now. So I don't want to work over fields of interest in arithmetic like QP, but rather I want to work over their algebraic closures to get rid of the Galois actions. And so practically what that's going to mean is that I'm going to have to work over rings like ZP bar, which is the integral closure of ZP in QP bar. And so this is some of the price you have to pay when you try to get rid of arithmetic, which is now you're faced with this kind of monstrosity, which is a non-Noetherian ring instead of just a nice DVR. But C'est la vie. And then X is my geometric object, which lives over ZP bar. So it's going to be, I mean, stuff is super general, but let me assume I'll just have variety. Technically speaking, all I want is finitely presented scheme. And so the picture is sort of similar to what I drew yesterday, except there could be singularities now. So here's kind of the picture for ZP bar. And here's a picture for X. There are, again, 2 points, one corresponding to the residue field at the maximal ideal, which is FP bar, and one corresponding to the residue field at the 0 ideal, which is QP bar, the fraction field. And then you have the two fibers. Let me just emphasize that there could be singularities. So let me call this XQP bar and XFP bar. And so usually in the Riemann-Hilbert story, one works over the complex numbers. And the Riemann-Hilbert problem is it gives a relationship between topological objects and differential objects on the same space. So the topological object could be something like a local system, meaning a representation of the fundamental group. And the differential object would be a vector bundle with a flat connection. And one precise statement of the Riemann-Hilbert correspondence in that setting is that if you have a smooth projective variety over the complex numbers, then complex local systems are equivalent to vector bundles with flat connection. The categories are equivalent. And so it gives a process of translating topological notions like local systems into this kind of more algebraic notions like vector bundles. We want to do something similar here, except the topological objects are going to have mod p coefficients. So we can't quite expect the output to live in Kirsig 0. So I want to work with topological objects over here. And the output is going to be algebraic objects, and they're going to be forced to live over here. Okay, so here's kind of a rough version of the theorem, which is that there's a natural functor, exact functor, between constructible sheaves. So I'll use the derived category notation. Derived category of constructible sheaves on this Kirsig 0 variety, XQP bar, with mod p coefficients. So a typical example of an object here would be like a mod p representation of the fundamental group of this variety. I'll call it RH. And the output is going to be some algebraic object on the mod p reduction. So, okay, these are declarations, but it's X tensor reduce mod p. These are étale sheaves, and these are quasi-coherent sheaves. And they, in fact, they satisfy a finiteness condition, which is called almost coherence, which I'm not getting into over here. And this functor has a lot of nice properties. So I don't want to make a long list over here, but let me just tell you some important ones. So the first one is RH applied to the constant sheaf. What does it do? I mean, in any kind of Riemann-Hilbert functor, I think that's the first thing you want to understand. And the naive guess would be you just get the structure sheaf, because that's what happens in the classical Riemann-Hilbert story. That's not what happens here, but rather you get something which sort of sees differential forms on X. But the name that's given to it is the perfectoidization of the structure sheaf.
In the classical case, you get not just structure sheaf, but you get with trivial connection.
Structure sheaf with trivial connection, right?
Yeah, yeah. So is this why you're getting some extra thing here?
Yes.
Because this to account for the connection?
Yeah, so, okay, after I talk about this, I'll get into what exactly this is an analog of. This is not an analog of the classical Riemann-Hilbert functor, but rather it's an analog of some doctored version. It's a modified version of the Riemann-Hilbert functor that comes out of Saito's theory of mixed Hodge modules. So that's where this was inspired by, but let me just write it. So this is some notion of perfection, meaning passing to the direct limit along the Frobenius, that you can make sense of in mixed characteristic using prismatic homology. So in mixed characteristic, there's no Frobenius endomorphism, but you still have the output of perfectifying along the Frobenius endomorphism. But the second property, which is maybe the more relevant one, is if I take RH and I apply it to a perverse sheaf, it has good properties. And so this is good commutative algebra properties. So it's almost Cohen-Macaulay, which you will recognize as the same word that showed up in the theorem over there. And okay, it also commutes with duality and pullback and push forward and blah, blah, blah. But I think
In usual situation, this equivalence of categories. So is there a statement of this sort here?
so the question was, can you say more than there being a natural functor? And the answer is not yet. I mean, there's a candidate. So there's a way to refine this into a fully faithful functor by keeping track of a Frobenius on the target. And then you can ask, what is the essential image? And there's a candidate guess, but it's just a guess right now. Yes. So the word almost showed up over here and over here. So this is almost in the sense of almost mathematics, which is something that Falting's invented. And so it's a source of a lot of humor. You know, you can do almost commutative algebra, almost algebraic geometry, almost differential forms. There are almost proofs of various statements. But anyway, it's a technical notion. It basically means that the failure of the statement to be true is annihilated by not only p, but all small powers of p. So it's the annihilator is really big, is what almost means. And so the relevance of this for the previous discussion can be summarized by just in just the following way. So relevance to previous discussion. So here's kind of a very easy lemma, which we didn't see anywhere, but it's kind of obvious once you formulate it. So take x to be any variety. Take x plus to x to be an absolute integral closure in the sense, like you take an algebraic closure of the fraction field, of the function field, and then look at the normalization. So it's the inverse limit of all finite covers. And then the statement is that if you push forward the constant sheaf along this map, it's a limit of finite maps, so there are no higher direct images. And you normalize it appropriately, so shifted by the dimension. Then this is perverse. In the sense of perverse sheaf theory. And so if you combine this lemma with the last observation over here and a little bit of knowledge of what the functor is, what you immediately get is R plus mod P, which is the Riemann-Hilbert partner of the sheaf. Is almost Cohen-Macaulay. So this is at least proving this Chordera vanishing theorem in the local case in the almost category. And this, again, in this technical almost sense of almost mathematics. And then you have to do a lot of work to go from almost statements to honest statements, which, of course, I'm not going to explain over here. But that's kind of roughly, very roughly, the idea of how this Riemann-Hilbert story is related to the commutative algebra side. And it's basically just this observation in the lemma over there, that there's a natural source of perverse sheaves related to the inverse limit over all finite covers. And if you apply Riemann-Hilbert to this example, you get some interesting consequences in algebra. OK. So I think this is all I wanted to say about this stuff. Since I have 4 minutes, I could try to say a little bit more about what this functor is and how it's related to the classical Riemann-Hilbert story, or I could just stop, leave it to the chair. OK, so I want to explain how to think about this functor. Because, as I said, it's not like a usual Riemann-Hilbert story. In particular, I didn't say anything about what this OX perf mod P is. But it's not it's not a sheaf, it's a complex. It's not just in degree 0, it has higher cohomology related to differential forms. And so what this is supposed to be an analog of is the following picture that comes out of the theory of mixed Hodge modules. So how to think of RH. So if you have a complex variety, let me just do it in the projective case. Smooth projective over the complex numbers. And then Saito has this marvelous theory of mixed Hodge modules, which provides a refinement of the usual Riemann-Hilbert correspondence. So I'm obviously not going to give you the definition, but I'll just tell you roughly what the picture is. So to any x, he attaches some category called the category of mixed Hodge modules. Whatever these objects are, they have forgetful functors to things we understand. So constructible sheaves on X with complex coefficients, and also filtered D modules, good filtered D modules. So generalizations of bundles with flat connection when you allow singularities. But it's not just a D module, it also comes equipped with what's called the good filtration, which is kind of the notion that makes the theory of D modules actually work. And then, of course, you can just forget the filtration. And so down here, oh, I guess I should, OK. So really, it's regular holonomic D modules. And so down here, you have regular holonomic D modules. Which is what you get if you further forget the filtration. And the classical Riemann-Hilbert theorem, or semi-classical by Kashiwara and Mepkut, is that those two are equivalent via the construction that takes a D module to its de Rham complex. But Saito's theory has this refinement where if you have a mixed Hodge module, the corresponding D module comes with a filtration. And so you can look at the associated gradient of the filtration. And the way good filtrations work is you get a coherent sheaf on the cotangent bundle of X, which is even GM equivariant, but OK. So it's getting much closer to algebra. So if you're an algebraic geometer and you've only taken like the first couple of courses, you've probably not encountered the notion of a D module. But you have encountered the notion of the cotangent bundle. And so you have a coherent sheaf on the cotangent bundle, and then you can further restrict to the 0 section to just get a coherent sheaf on X itself. And I'm doing the streak restriction to get some normalization right. And so the output of this entire story is you get at least a correspondence, if not a functor, from constructible sheaves to coherent sheaves. This is a correspondence, meaning it's not everywhere defined. And the Riemann-Hilbert functor up there is essentially an analog of this correspondence. And so that can at least help you figure out what kind of statement should be true. So for example, if I take the constant sheaf over here, it comes from the constant sheaf over here, and I run it through this procedure, what I get is the exterior algebra on differential forms. And therefore, this perfectoidization thingy is some mixed characteristic avatar of the algebra of differential forms. And so let me just write that, and then I'll stop. So this is the analog of RH above.
You said that there was a fully faithful version.
Yes.
That would be an analog.
So I don't actually.
Yeah, that's this.
Correct.
So can you upgrade the theorem to make it analog to fully faithful?
So Paul's question is, can I upgrade this arrow over here to make it fully faithful somehow? And the answer is I don't actually know. In the mixed characteristic picture, the full faithfulness comes by recording a Frobenius. And don't quite know what the characteristic 0 analog of the Frobenius should be. Right, from here. But not from here. Okay. Anyway, sorry, that's all I wanted to say. So let me stop first.
Any questions? So when you're describing the characteristic P group,
Mm-hmm.
then like at some element, you put some elements in some small place, and then you did the Frobenius and so on. But in this description where you got to here, proving this sort of almost Holland-Colley, you didn't use the Frobenius. So did the Frobenius just happen like you went to Prismatic Homology and then the Riemann knew enough about Frobenius to do what you wanted? Or?
So the almost Cohen-Macauliness is actually relevant in putting yourself in, it's the analog of step 1. So step 1 was a statement that after a finite cover, you can make the image finite. Finite means that the image is annihilated by a power of every element of the maximal ideal. And so in the maximal ideal of prism R, there are sort of D elements that come from R, which you can handle by induction. And then there's an extra arithmetic element that comes from U, and that's handled by this almost Cohen-Macauliness. Correct. Once you put yourself in the finite length situation, that's when you start using the Frobenius. Thanks. Yeah.
Any other questions? Yeah, so in the usual correspondence for shifts, limited correspondence for shifts, the reverse shifts also have a nice image, which is just D modules rather than complexes.
Mm-hmm.
And here you say that you also can describe what happens in the reverse shift, and it's almost Cohen-Macauliness. So is there an analogy between those two statements?
So the question was, the image of perverse sheaves under this functor is regular holonomic D modules, which is a nice description of the image. And is there something similar up here other than what I wrote about almost Cohen-Macauliness? And so I mean, there is.
Is it analogous, what you wrote, is it analogous to this statement that I quoted?
There's more to it than what I wrote, and then it will be analogous. So there is really a T structure you can write down on the target. And you can prove RH is T exact. And what goes into it is the statement that I wrote together with the duality compatibility. Yeah.
Any other questions? So let me ask, so in this more limited setting, so there was this Riemann Hilbert by Emerson Kissian.
Uh-huh.
So I guess it's
Right, that's the mod P version.
mod P, yeah. So how was this released?
So the thing that Jacob and I did actually, the statement makes sense for any p-adic formal scheme. And so if you plug in a mod P p-adic formal scheme, you get something that's essentially equivalent to the Emerton-Kisin correspondence. It's like a covariant version of what Emerton and Kisin did.
And it's basically the same.
Basically.
So there's also a question that I forgot to ask yesterday. So can you explain the name prism?
I'm being recorded, aren't I? Yes. Well, OK, so there's this. I don't know how much you're going to buy this, but I'll try. So basically, when you in prismatic homology, you have some x, and then there's some base prism a comma I. And then the output is this complex, prism x over a, which has a bunch of different specializations to different cohomology theories. And so the picture roughly is that this is spec A. It has this kind of distinguished face corresponding to A mod I. X lives over here. And the output is this prismatic homology, which sort of has all these specializations. So it looks like a prism.
Thank you.
Yeah.